Good evening, ladies and gentlemen, and welcome once again to another episode of Love2D Tutorials. I am your host, and I will be guiding you through the wonderful world of Lua and Love2D to create graphical masterpieces. Today, we're going to take the circles that we had in the last episode. We determined when they would collide. We're going to provide a collision response for these circles. And from that, we will, maybe not on this episode, but the next episode perhaps, move to resolution of the rectangles as well. So we're headed towards a collision response system. And this is exciting. So let's get started on that. Remember last time we did the circle collide, and we had that in the utils directory. I'll keep that in the utils directory for now. We'll pull it out into some kind of physics or shape kind of module or something like that. Utils directory. I mean utils module. Yes. I want to make this. I want to change this to, instead of circle collide, I want to do circle overlap. Circle overlaps. So a circle overlaps. And what I want here is, instead of returning whether or not the circle, so in other words, instead of returns Boolean, which is true if circles overlap, false otherwise. Yes. Yes, I want to return also, since Lua, the wonderful world of Lua, we can return multiple return values from a function call. So the next thing I want to return is if true, if colliding, then also returns a what we would call a minimum separation vector. Okay, so in order to do that, we're going to need to utilize actually create a few things in vector 2. Let me show you. So we have this to do other vector functions. Well, we can erase that because we're about to embark on that. Now, I want a function that will take a vector 2 and that will determine what I will call its magnitude, and we'll just say mag. And we will go ahead and, so it says calculates the magnitude of the vector. And say, okay, so the magnitude of the vector, I'm going to bring up paint.net as I did last time, and going to do a very crude drawing here. So the magnitude of a vector, if we look at a vector, we say we have a vector that looks like this. So there's our vector. It points in a direction, of course, a vector. If you learned from Despicable Me that a vector has a magnitude and a direction, right? So our vector here is composed of actually two pieces, and that's what we're representing in our x and y. So if we drew an x and y axis, say like this, there was our y axis, and then this would be our x axis, say, if I was able to, actually I can hit the bar there. Let's do that again. Let me draw it from here just for fun. Doesn't have to be, but I'm going to just start it from there. There we are. Now, so we have these axes, the x and the y axis. This is the y axis. This is the x axis. So we have these coordinates, right? So that's all a vector is, really. We can assume it's from, we could say it starts from the origin here, if we desire, which is what we're doing here. And then it goes to a point of x and y equals some value here. So this is our x, y coordinate. And this may be simple for you, but I'm going to go over it anyway. I'm going to take the pencil here. And so what's nice is we can determine the x portion of this, of course, by just this number is going to be the x portion of this particular triangle, because we're going to form a right triangle, because these two axes, the x and the y axes, are always perpendicular to one another, at least in the way that we do these particular things. And that can be true even if these axes are rotated, because if you rotate one axis, then you can assume the other one is anyway. We're creating a right triangle. So this right triangle, and if I can find my colors, and they're right here. So the x portion of this little fellow is, of course, down here until we get to about there, I suppose. And then the y portion is, of course, the height of this little fellow, right? So there we are. We have something very, very interesting. And if you remember from school or from university, of course it would be in grammar school or whatever, but we have, and I have no way to make a, oh my, that's a horrible, horrible font. X, and we'll have this caret, and I'll indicate that as x squared plus y squared equals c squared. And that is, my friends, that is our wonderful friend Pythagorean's theorem. We love it because from that we can calculate c squared, or we can calculate c, which, so we know this is x, we know this is y, and this is c, and what is called the hypotenuse. In our case, for the magnitude of a vector, the hypotenuse is what we want, because that's going to be our magnitude. We need that. We need to be able to calculate that magnitude, and I'll show you why later. So we've already seen how you do it. It's going to be the square root of x squared plus y squared. So that's all we're going to return here. So if you remember previously, we have this power and square root here. We declared those as local, and that increases the speed of Lua. Of the calling, apparently, I suppose, because it doesn't have to dereference the tables or whatever. But supposedly, I don't know if that works or if that has any bearing, since we're using since Love2D uses LuaJIT. But anyway, this makes it easier to write. So I'm going to copy these into vector2, and we'll put them down like this. So all we're going to do is return the square root of the power of self.x squared plus the power of self.y squared. You see? And that is our magnitude. So that's great and fantastic. So now we have the magnitude. We can get the magnitude of a vector. There's another thing that we're going to need, and that is what is called calculate the, you can call it the normal, or really it's called the unit vector of this vector. And that is, let me just type this. Unit. So what we'll do here is we'll return a new vector. So vec. And this is going to be, and we'll also want to do a local. We want to calculate the magnitude of this vector first off. So we say self colon magnitude, or mag. There we are. So a unit vector simply has the distinct trait that if you calculate the magnitude of a unit vector, then that vector will be the magnitude of it will be 1. So that's what we want to do, and that is simply going to be the self dot x divided by the magnitude and self dot y divided by the magnitude. You'll see. So that's all we need to do. And that will return a unit vector, or a vector of unit 1. And why do we want to do that? Well, with a vector of unit 1, or a vector, so we have then is a vector that points in the same direction as the initial vector, but its unit, or its length along C is 1. Therefore, all we have to do to make it any length we want is multiply it by any number that we want, and then we know immediately the magnitude of it, which will be great for what we're going to do, because we need to find a separation for our circles when we do this. So I think that should probably do us for the circles, or for the vector. So let's go back to utils, and so we have circle overlaps. So what we want is, we've got the distance, and we are calculating the square root of that distance, which is fine. So then let's say, again, if distance is less than, well, let's just do this. If distance is less than, or actually, let's turn this into so now that's going to be our Boolean. So if these things overlap, then we're going to do something, right? So if they overlap, then we'll do something else. We're going to return 2 values, and that will be false. They don't overlap, and we'll return a null, which means no vector at all for now. But if they overlap, we need to basically create, what we need to do is we need to create a vector that points from, say, from circle 1 to circle 2. In order to do that, we just say, let's call it local C1 to C2. And that's going to be simply, do we have vector 2 in here? We are not including vector 2. Let's include vector 2. Where did we have? I know, I'm lazy. It was in Sprite. We did include vector 2 here. I'm going to grab that, and I'm just going to paste it up here. So now we have vector 2, and we'll create one down here. So C1 to C2 equals vector 2, and to create a vector that points from one point to another, so if we want to point from circle 1 to circle 2, we simply use circle 2 as the reference, and then we subtract circle 1 from that. I'll show you what I mean. Circle 2 dot x, and then we subtract circle 1 dot x from that, and then the same for the y values. Circle 2 dot y minus circle 1 dot y. And then for that, then we can say the distance, or the magnitude of this vector, is we can just do this. C1 to C2 magnitude, just like that. And then we could actually return, let's actually do this. We'll just do a test here. Return overlaps. So that should give us the same exact thing that we had last time, where we should be able to say these circles overlap or they don't. So see, we're just verifying that it does indeed do the same thing. So that's good. So let's get back to it. So if overlaps, then what we want to do is we want to grab this vector. So we'll say your local, and we're going to make a unit vector out of it, like I said, which means that the actual vector, the length of that vector is going to be 1, because we're going to control that length. So we'll say C1 to C2 dot, or not colon unit. So that's our unit vector. And what we really want, so what we're going to return is whether or not the circle overlaps. And then we're going to return a vector that, if applied, will push our circle back out to where it does not collide with the other circle, if that makes sense. So we need to also do another, we need to add another thing to our vector 2, and that will be a multiplication function. Call it mul, and all this is going to do is self.x equals self.x times the multiple. So we're going to scale the vector is all we're doing here. Self.y equals self.y times multiplication. So we have this unit vector, and we know that the what we call, and if you read any of the papers, what you'll see is the minimum separating axis theorem, I think is what it's called. But we know the minimum amount to move the centers of these things away from each other is going to be the circle 1 dot radius plus circle 2 dot radius. And that's going to, so that when we take that unit vector, when we multiply it by the sum of these two radii, we will have a vector that will ensure that our circles do not overlap, the minimum separation vector. So here we would return true, and then we would return unit. And this should actually still work, except vec. What am I doing? Vector 2. Oh yes, of course. I missed that. Yeah, right here. There we go. I'm sure you were screaming that the whole time, weren't you? So yes, and of course vector 2. I'm mistyping all over the place, aren't I? Run it again, and boom, and mul. Oh yes. Once again, I'm talking too much, aren't I? But that's the point of these these tutorials. Okay, so we're still good. We're just not using that in an additional return as of yet. So let's go into the test here. And let's do this. We're gonna grab both of those return values. So local overlaps, and we'll call it sep. So if overlaps, then and we'll make sure that still works, which it will. See, we're just grabbing that. So if it overlaps, then our separation vector should be in there. So what we okay, so this is going to get a little bit tricky, but let's see if we can figure this out. Self C1 dot x I'm probably going to get this backwards. But let's go ahead and try it. Self c1.x equals... so we're let's see, where did we point the vector? We said... Oh, it was in utils. So we're going c1 to c2. So it would be self c1. We say self dot 2 dot x minus step dot x, I think, and do the same for y. Get ready, ladies and gentlemen. This is not going to be pretty. I haven't tested any of this, by the way. Oh, look at that. See? It works. You can see I'm trying to go inside, but it will not let me. See? So I got it right. Excellent. So you can tell that it's just moving our circle out that minimum amount. Now, that's assuming that this circle is a static circle and doesn't move at all either. If we wanted to, and maybe I don't do that right now, but if we wanted to, we could actually we could have it such that when this penetrated this circle, we would move them both half of that amount. So we could you could get, instead of returning, maybe you would just, I'm thinking here, if maybe you just return, no, we could get into math and all that kind of stuff, but we could, in other words, what we could do is, instead of this, we could actually say, let's try this real quick. This isn't going to work, but let's try it. And that's probably not going to work. That's not going to work. Let's see what this does. Yeah. Actually, I think it would be plus, wouldn't it? Ah, vectors, such a wonderful thing to play with, isn't it? You can see that. I know what's going on there. We could say that, what's this? Okay, never mind. You know, really, you should be able to do that, but it's, yeah, actually, you're really wanting that over how much overlap it is. So you would take, yeah, okay. So you really want the difference between the total circle radii and the actual distance. So you would do something like, you would subtract that actual distance from circle 1 to circle 2, and then whatever you had left over would be the minimum amount to push the other circle out so that it wouldn't. And of course, that's probably because we're doing this. I'm sure I'm not doing a very good job of explaining it, but in any case, see, you can see it works. So what I just did was, So we have that unit vector, and then so we know it's just a vector with a direction and a unit 1. So we want to make it a certain size, but we want to basically what we want to know is that minimum amount to push the circle or this guy back out so that it doesn't collide with circle number 2. And that's going to end up being the distance at which the difference between the current distance between the two circles and the distance, the non-colliding distance, the minimum non-colliding distance between the two circles. Gosh, that feels complicated to say, doesn't it? But all it's doing is just getting the amount of penetration that this other circle has whenever it comes into this loop. So we get that amount of that minimum amount of penetration. So a vector that's going to be, you know, smaller than the one that's than the minimum separation between the two circles. Say this was circle 1. Oh, that's horrible. And this was circle 2. So then we would say that this particular vector would be that, you know, if this was R1 and then this had a radius of R2, then this value or the magnitude of this vector would be R1 plus R2. That would be where we would want it. But if this particular circle was penetrating, then we just want to know how much it's penetrating, and that's what this does. So this just gives us that minimum amount of separation. Yeah. And really, I think what I would rather do is I'd rather be able to add these instead of subtract them because it makes more sense to me. So in other words, we're just going to reverse this vector. So it's going to go from circle 2 to circle 1, and that way the vector will move in the right direction. And that way we can just add it because it should be a positive separation vector, and you can see that it still works. So you know, the other thing you could do, if you wanted, you could add mass to these two circles, and then you could base your separation values off of the mass of the two circles. Or you could just say you're going to get half of that separation, and then the other circle could get, if you want to be able to move the other circle some, you could say, well, he's going to get half of the separation, but of course since it's in relation to pushing back that way, then we would have to do negative here. And then that should allow us to push these circles along, you see. But like I said, really what you would want to do is you would want to base it on the mass of each circle if you were going to be physically accurate. But in any case, that actually works. I'm going to leave that in, and we'll comment it out. That's what I'll do. But also we'll put this here, and I'll add this. So I'll comment it, and then I'll say, you could do this, or you could apply half the separation vector to each of the circles in question. But ideally, it should be based on the relative mass of each circle. And maybe what we should do is instead of circle overlaps, we could do circle collides or circle collide. Of course, again, it depends on which circle you're talking about as far as what's going to happen, because right now, so we could say with this only the first circle will be moved. right? There's just so many ways you could do this. I'm pausing because I'm trying to think about how we might do this instead. And maybe we should have a function that just says u dot circle collide, and we could have circle 1, circle 2, maybe. And then we could, instead of how we're doing it, let's say this collides 1 with 2 and currently applies the, I have an idea. So this will collide circle 1 with circle 2 if they overlap. So what we can do then is let's grab all of this, and I will show you what I'm talking about, and we'll return true or false here. So we'll say the same that we did here. Circle 1, circle 2. So we're going to just use this up here and here. So if it overlaps, then we're not changing color here. We're just doing the separations. And that. And then we will return. If they want to know that it overlaps, we'll return that. And if they overlap, it will apply a separation to one or both circles. And I'll show you what I'm talking about in a minute. We're going to change something. It's going to be really cool. Returns true if the two circles collided. False otherwise. Let's get this put in here. So we'll say circle collide, and then this will go away, and then we can just basically say if circle collide. Let's make this plural. If circles collide, tonight at 10, 2 circles collide. Devastation left in the wake. There we go. Oh, wait. Gotta keep that else in there. Let's run it and see if it works still. Yeah, okay. Yeah, we gotta get rid of the self and make those circle 1 and circle 2. Circle 1, and let's just do it like this. Circle 1, grab circle 2, and I'll use the magic of the editor. And now, here we go. Now let's make sure it works. Okay, so that's working. So we're doing the collision that way. So we have 2 functions now. We can test to see if one circle overlaps with another one. And then the second one is we can actually collide those 2 circles. So now what I want to do is I want to say we're gonna change this so that we can basically create this down here if we want to. So we'll say parameters circle 1, circle 2. Not circle. Circle 1, circle 2 are the circles in question. And then we'll say separation. We'll just call it ratio. And that will be a number from 0 to 1. that affects how much of the separation to apply to circle 1 versus circle 2. And I'll show you what I mean here in a minute. Ratio, so we'll say that ratio, if they don't put in ratio, then we need to do this, ratio or 1. So that ratio is how much of that separation vector is going to be applied to circle 1 versus how much is going to be applied to circle 2. So, and now we come to the other question, and that is, with this overlap, do we return the, so we have the two, let's do this. We're going to return 3 things from here. Also returns a minimum separation unit vector and the minimum separation magnitude. That makes it easier for us whenever we come down here and we want to apply a particular ratio, then we can do it this way instead of. So all that means is we just say, instead of doing this, we'll comment it out. We'll try this out, but we'll return 3 values. We'll return that, and as a matter of fact, I don't think we even need to do that. We'll just return 1 otherwise. So we're returning that unit vector as the second piece, and then the third piece is the magnitude of that unit vector. We really don't, I don't know, we really don't have to do it. We really don't have to do it this way. We could do, yeah, we could just do it like this. So let me just, let me go back to this. Yeah, we'll just do it like this. So that's just going to return the separation, the minimum separation vector. And then from here we'll do this. So that ratio will affect circle 1, and then 1 minus that ratio will affect circle 2. And we'll say, we can go up here, we can say if ratio, so we want the ratio to be less, we want it to be 0, between 0 and 1. So if it's less than 0, then ratio equals 0, and we could say, so let's do else if ratio is greater than 1, then ratio equals 1. That's just a safety check. We don't really have to have it if we obey these rules here, but I'll leave it in. So we'll say, ensure that the ratio, I want to put ration, is between 0 and 1. You see? So that's what we're doing here, and we'll need to add parentheses here. Click, click, click. Let's check this and make sure my math is working correctly. End expected near function. Did I do this wrong? I did. So that is with a ratio of 0. So what we could do in here is we could say, where did we go? Test. We could say circles collide, and we could put a ratio of, say, 0.5, and that would mean half of the separation vector will go to pushing out circle 1, and half will go to pushing out circle 2. So we can push, should be able to push the circle, except that I forgot the signs are different, and we also didn't change this. I'm getting ahead of myself, ladies and gentlemen. And this is going to be negative because remember that it was in relation to circle 1 anyway. So now we should be able to push this one about half. But if we made, since that circle's bigger, so we can basically use that and do like a mass difference if we wanted to. We could say that really most of it is going to be circle 1. A little of it, so it's going to be harder to see. It's going to be harder to move this guy. Or we could do like 0.2, and it's going to be easier to move the big circle. See? Beautiful. I like it. So for now, we'll just leave it at 1. And I think for now, what are we looking at? We're looking at 40 minutes. Oh my goodness gracious, ladies and gentlemen. I'm so sorry to kept you so long, but we do have something that looks kind of cool, and when we get back, I think the next task will probably be applying what we have learned to these rectangles. And with that, I leave you until next time.